So I was asked to speak about the impact of initial state parameterizations on isobar collisions. And to do that, I thought that I maybe give a short introduction on like what's going on in heavy ion collisions and also what kinds of observables we have, and not just the observables, but because I mean, you heard already, for example, in Robert's talk that doing full hydro is quite expensive. What kind of like initial state predictors we use to already get an idea of how those observables will look after running the hydro. And then I will show you some results based on those initial state predictors. And then in the second part of my talk, I'll introduce shortly a hydro framework I'm working on, and then show you some results using this hydro framework. And if you have questions or comments, just as always, interrupt. And can we have a discussion? All right. So I'm sure you all know this picture with like the stages of a heavy ion collision, where we start out with like the colliding nuclei, have a QGP phase, and at the end we measure some particles in the detector. So let's quickly go through the phases and start with the do it chronologically and start with the initial conditions. And here we have already heard, so I'm not going into much detail here, that you can model the initial conditions by a plethora of different models like Glauber model, IP Glasma, Trento, what was explained in great detail yesterday by Robert, or the color glass condensate. And on top of those models, you can add a pre-hydrodynamic modeling stage, for example, via free streaming. In this case, this would be the no interaction free streaming, but you can also do stuff like this strongly coupled ADS CFD correspondence kind of thing that was introduced yesterday. And then what's, I would say, mostly used is Trento. And I'm not going over again how it works again, because they simply can check this slide from yesterday. But what's maybe important to keep in mind is for later on is you have certain parameters. One is this P, which is this reduced thickness, which tells you how you combine basically your two wounded nuclei. Then you have this parameter K that controls how much fluctuations you have. You have the nucleon width W. And then when you place your nucleons, when you sample your nuclei, you have this minimum nucleon distance D. And then this also was touched upon briefly yesterday. You have two further parameters M and V that are related to a subnucleonic structure. So that this M is the number of constituents that you, for example, put in your proton or neutron, and then the width of those constituents is the V. All right. So now we can move on to this next phase of the heavy ion collision, which is this QGP phase. And this was also already briefly introduced yesterday. And this gets modeled by hydrodynamics, which is based on the conservation laws, which usually or always is this conservation of the energy momentum tensor plus some additional conservation laws if you have other conserved currents, such as a baryon number current. And from this, if you plug in the energy momentum tensor, that usually looks like this. If you do the tensor decomposition based on the Landau matching, you get equations that look like this. And as you can see here, we get 4 equations, but we have a lot more degrees of freedoms, like fields like this bulk and this pi mu nu, where we need supplemental equations to close our system of equations. And those are one possibility of obtaining them are the second order Eisel-Stewart equations, where I have them here now in a more condensed version than yesterday in the 40 moment approximation. This is, you can have a lot more terms here and then get the full 40 moment approximation, but I just want to demonstrate roughly what the idea behind them is, so we don't need all of the 40 moments. And you start out with, so this one is for the shear, the second one is for the bulk. They work in the same way, but the bulk is easier because it has fewer indices. So let's look first at the bulk, and the green term is what you basically start out with, is the ideal hydrodynamics case, which just tells you you don't have any viscous corrections and you have like pi bulk equals 0. What you then can do is you can add this red term, which is the so-called Navier-Stokes term, which introduces this zeta, which is the this viscosity that was already talked a lot about like yesterday and all the other days. And this allows you to have this bulk this out of equilibrium quantity to be non-zero. But if you just use the red and the green term, what actually you can show or you find out is that your equations can and will violate causality, and that's of course not something desirable. So what you do is you introduce this blue term, which has this relaxation time, which makes sure of when you choose the relation between the bulk and so the relaxation time and your viscosity in a proper way, you make sure that you don't violate causality, and this allows your bulk pressure to relax slower to back to the equilibrium value. And you don't need this instantaneous reaction that basically gives you the shocks and the violation of causality. All right. And then as a last step, we need this phase where we basically produce the particles that we then measure in the detector. And one way of doing this is a so-called Cooper-Frye freeze-out prescription, where you simply say that your particle distribution at some space time point x is simply given by some distribution function that depends on your hydrodynamic variables. And if you then want the full amount of particles you measure in the detector, you simply integrate over this freeze-out surface. And the so-called freeze-out surface is usually defined by a temperature where you would say that you switch from having a description that's based on quarks and gluons to a description that's based on like hadronic degrees of freedom. And one way of choosing this distribution function is that you say this F is a sum of like an equilibrium distribution that's like for both just a Bose or Fermi distribution, and then you can add various correction terms that are give you the corrections due to the presence of like shear and bulk viscosities and the corresponding fields. And on top of this, you can have or introduce even more physics by having, for example, two freeze-outs where you have a first a kinetic and a chemical freeze-out. Or what you also can do is like hadronic afterburner or rescattering, which is, for example, this mesh code that was mentioned yesterday, which is implemented in the triathlon framework. All right, so this is now basically was the first part where I hope I gave you like a rough overview of what's going on in the collision. And now I want to take a look at like what observables do we actually get out of all of this.
So for the bulk correction,
yes.
Can you discuss like in which phase space the shear is important, which space is bulk correction is important? Let's see the hydrodynamics relation. What is the role for this bulk correction and shear correction to the distributions? Like, just want to know, or get some idea. Which situation is important?
So from my experience, I would say that like those corrections too, for example, if you look at stuff like total particle number, they're not really important, but they can modify the PT dependence of your spectra. And then if you look at the end, for example, they get more important.
But for the bulk correction, I mean, there are various formulations of the bulk correction. This is one of them.
Yeah, of course. This is
and they give actually quite different results at low PT. And the bulk effect is proportional to the mass of the particles that you're looking at. And for massive particles, there can be very significant modifications at low PT, akin to a change in chemical potential.
But the total particle number is independent, sort of there's a
no.
But the bulk.
Okay, but
by construction, isn't it the sum of zero?
But in the partonic phase, is bulk correction important? Like in the QGP evolution.
So you kind of misspoke a little bit. Like, you know, you need to be describing the same physics two different ways. So we're switching description from fluid degrees of freedom to particles degrees of freedom, which have to be hadrons, so that's what we deal with at the end.
Right.
So your phase transition to hadrons has to happen before you change its description. You have to, hydrodynamics can describe the phase transition, both phases, but you have to at least believe that you are in the hadron regime already before you change its description.
Because we don't have a microscopic description of the quadron plasma and the hadron diffusion state. We only have a microscopic description of the hadronic phase activity, which is sufficient.
So this is all just hadrons.
Yeah.
This is all the hadronic system that he's talking about at this point when you're switching.
Okay, so but
And the word freeze out in this context is also slightly misleading because it's now mostly used as a change of language from fluid degrees of freedom to particle degrees of freedom.
but the shared bulk with this correction in the QGP phase, I can imagine you don't
You
can
don't need
you
it because
So
this happens on the surface,
yeah,
which
you-
is not.
The correction in the QGP phase comes from those additional equations of motion. And this is only for this transition when you
Okay.
switch from here to particles, basically. You need to account for the fact that in here you have a non-zero bulk pressure. And then this leads to
some effective correction.
yes, like to a correction of your particle or your hadron distribution function that may look like this, or you can parameterize it in a different way, but that's the basic idea. Okay, so and now let's look at some observables we actually have in the experiment. So in the first one and the most obvious one is the N charge, which is basically that you measure or count how many particles do you have in your detector, how many particles do you actually produce. And the initial state predictor, so a quantity that you can already define on the level of the initial condition, which you can use to predict this, is at the initial state total entropy. You can show this by looking at the ideal gas, and then you can simply see that the entropy is proportional to the number of produced particles. And you also see this, now this is taken from Giuliano's PhD thesis, where you can also see this derivation. And here you see that if you run, I'm not sure exactly how many hydrogen events those are, but if you sort them by entropy and then plot simply the entropy versus the produced number of produced particles, you see that there is a strong correlation, which shows you that this is a good initial state predictor of your produced particles or for the multiplicity. And the second observable is the so-called mean PT, which is simply the average momentum of your measured particles. And there the initial state predictor is the energy of your initial condition or your system size. And again, here you see the correlation between the mean PT and the initial state energy for fixed entropy. So all those events are at one fixed entropy. You see again that there's a strong correlation. And the reason is, you can imagine this, that if you have two events with the same entropy, here is A and B, and one of them has a much larger area than the other one, the gradients here will be much smaller than here, which will lead to a lower mean PT. And of course, if you imagine you have to pack the same amount of entropy in a much smaller area, the temperature will of course rise. So, and with temperature also the energy. So you see you have this correlation with energy and this anti-correlation with the radius. And then another observable that already has been talked about quite a lot is
I have a
the
question. So all this is done with triangles, correctly? Like
you mean those plots or those predictors?
to predict, I mean, yeah,
So yeah, you can do them with Trento. The results I will show are done with Trento, but
I mean,
you
those,
can-
you have those, if you use another way to define your structure, do you have the same correlation?
Yes,
yes.
that's the whole idea.
Yes.
This plot was only Trento. This was only Trento.
Well, this is
Compared with
Trento plus some hydro.
Yes. The
Yeah, yeah.
initial conditions were from Trento.
Yeah. So yeah, this is Trento plus some hydro.
It's an idealized.
Yes. So and
So it's actually, the entropy doesn't quite require.
Fernando.
okay, and then an observable that's already been talked about a lot is the flow harmonics, the Vn, where you can look at the talk by Jean-Yves, but basically the idea is you have some initial spatial anisotropy, which get converted in some momentum space anisotropy. And here the initial state predictor is a so-called eccentricity. And here's the equation for the epsilon 2. This is basically just the weighted average of your initial entropy distribution. And this is a measure for how much of an oval your initial entropy distribution is. And this you can generalize this for epsilon n, where here instead of x squared, you just put in, for most cases, an x to the power of n, and here as well. And here you can see on the x-axis this eccentricity, and on the y-axis the V2 after hydro, so the flow coefficient for two different centralities, and you still see that it's not as well of a correlation as, for example, with the entropy and the n charge, but it's still a reasonable initial state predictor, I would say. And it also holds over this wide range of centrality. And as a final observable that has already been shown, for example, by Giuliano in his first talk, or also yesterday by Robert, is this Pearson correlator. So the equation looks a bit complicated and maybe a bit scary, but the idea behind it is a really nice one and quite simple one. So if you now imagine we have two prolate or two oblate nuclei, then, and we look at the very central collision, so with full overlap, there are two possibilities. You either can have a body-body collision or a tip-tip collision. And if we now look at the body-body collision, you will have a large area of overlap that's very elongated. So with what we heard before, if we apply this to here, we have a large area, which means we have low mean PT, but it's very elliptical. So we will have a large V2. And if we now look at the second case and rotate those nuclei by 90 degrees to get a tip-tip collision, our area of overlap is basically a perfect circle. So we will hardly have any V2, but we have a very small area of overlap, which means that our mean PT will be very large. And this means that the V2 is anti-correlated with the mean PT. And this means that if you have like triaxiality in your system, this Pearson correlator is an observable that's actually sensitive to the gamma of your nucleus. And you can also see this in here where you, for example, have the sign change in this Pearson correlator. This is a star preliminary in the uranium-uranium collision that has a non-zero gamma, and the gold Pearson correlator doesn't have the sign change because it's not as much deformed. All right, so are there questions to those observables? Is it clear what you can do with them? Yes.
No, I just wanted to point out that the credit for this idea should go to Bosch.
Yes, so I just took the plot from Giuliano, but
This plot's from Star.
yeah, so this plot is from Giuliano, and I stole this plot from Giuliano, who stole the plot from Star. So
Project proposed this is definitely proposed the observable,
Yeah.
but the interpretation, I think is
Yeah.
Giuliano's.
For deformed nuclei, I'm
Yeah,
not sure
but
you
I
talked
think
about that.
this is definitely-
Put them more reference.
okay, we'll have more references.
Okay, Piotr's not good today. He only showed up on Monday.
Okay, let's go.
Okay, then let's continue to some results. So now to see what kind of impact the Trento parameters I've talked before and the nuclear structure parameters we all talked a lot about already have, we came up with a set of like batches where we vary Trento parameters one by one, and where we vary nuclear structure parameters. So we have one baseline of zirconium, and then we have 5 cases of ruthenium, where we basically start out with the same parameterization as the zirconium, except for different radius, and then one by one change the different quantities. So from here to here, we, for example, change the nuclear spin, and we change the beta 2, the beta 3, and the gamma at the end. And then we take the ratio of every case to this baseline case. Yes.
You take the Wood-Saxon parameters for protons and neutrons the same or different?
The same, I think. So it's the standard Trento.
Yeah, but you can also, like, if you want, for example, have a difference gain, you can.
No,
use a different one.
No, I think it should be the same. And then basically we take every possible combination of those 8 cases with those 5 cases and run 20 million minimum bias events per combination and calculate basically all of the before shown observables plus some more on top. And now I'm going to show you a selection of those. And if you're interested in more observables, I have 20 backup slides with as many observables as you want to discuss.
So this is 20 million initial conditions or 20 million?
20 million initial conditions.
Okay. And when you say observable, you use the fact that to establish a
Exactly.
linear relationship between the observables and what you are
Exactly.
calculating.
Exactly. I'm basically using those correlations I shown for like n charge and entropy and all of this to use this as like, yeah, initial state predictors basically. All right. So then let's start with the first slide and the first result, and let me walk you through it. So those are the multiplicity histogram ratios for ruthenium divided by zirconium. And then you can see here that in one panel, you always have the five cases color coded. The blue crosses are the star data, and you have 8 panels corresponding to the different Trento settings. So this is the default setting. Here you have where we change the p-value, so default is p0. This is p equals 1 minus 1. Here we change the nucleon width. Here we basically have a Trento run without multiplicity fluctuations, where we increase the k by a lot. Then here we increase the minimal nucleon distance to 1 Fermi. And those 2 panels are with 4 subnucleonic partons, which in this case are 0.1 Fermi large, and here they are 0.4 Fermi large. And the slides will always have the same structure, and now we can look at some results.
What's the default value for W?
The default value for W is 0.5.
Okay, and for D?
For D is 0.
No, Trento without any separation.
Yes, that's the default value given by Trento. All right, so then let's maybe first look at this default panel with just the lines. And you can see here, so we have 5 cases, case 1, 2, 3, 4, and 5. And here I've snipped the important part for this actually is when you look at the difference between case 4 and 5. Because you see in all of those panels, cases 1 to 4 are bunched up and are basically always on top of each other. And the only case that's an outlier, which is basically always flat, is case 5. And the reason for this is the difference between case 4 and 5. I don't see this later part, you just have to believe me, but basically...
At home, they can see it.
At home they can see it, very good. All right.
Just the projector.
Okay, but I mean, okay. The difference is only here in the neutron skin. I think this will go away. Ah, yes. All right, great. Now we have everything. So yes, the difference is only in this A0, so in this neutron skin thickness. And you see that if you say
No, the radius.
No,
yeah,
the difference between 4 and 5, you only change one thing at a time.
yeah, between
That's the only
4
thing that
and
changes.
5 here, the radius stays the same, and the only thing that changes is this neutron skin thickness. And then,
Can you remind us what is 100 when red spin, right?
sorry?
The units.
Yeah, is that entropy or particles or what?
No, this is the in charge, not the entropy. This is always the in charge. Sorry. Yeah, so this is the ratio, and this is the in charge.
But the denominator is which one? These are all ratios.
Denominator is case 6 always.
Yes, you always take the ruthenium divided by this baseline zirconium case. Okay, so basically you can see from all of those plots that this neutron skin thickness is the dominating nuclear structure parameter for this multiplicity ratio. And the second thing you can observe here is that in terms of Trento parameters, basically if you vary this V, the W mainly, and this P, you can change this drop here. And I think my interpretation of this is basically, you, for example, look at the default case and then compare it to W1.5, where we enlarge the nucleons by very much, or from 0.5 to 1.2. It's basically what happens is all the ratios go down to and go further down direction of unity. I think this comes down to if you just increase your nucleons more and more, you simply will wash out all the like difference in nuclear structure you have in your two nuclei, because if you just put huge blobs everywhere, there's no difference anymore. And this is the reason why if you, for example, have a different beta or different A, it doesn't really matter anymore, because these differences just get washed out by the huge nuclear size.
And you probably said it, but I slept through it. What's the crosses?
The crosses are the star data.
Oh,
And so basically, roughly speaking, one could maybe say that the dominating thing on the side of the Trento parameters here is the degree of sharpness of your QGP, if you like. I know it's not really well defined, but you can say that if you have like a smaller partons or smaller constituents, like a small W, you have a spikier QGP, and if you increase your W to a very large number like this, you will have a very smooth QGP that washes out the difference between the ruthenium and the zirconium.
Well, it almost looks like it's more about how fast it falls off of the edge. Because you either change the skin thickness parameter of the point distribution, or you make the nucleons bigger, which also makes it fall off slower at the edge. Would that not be also a possible interpretation of this? Instead of the granularity spikiness in the middle,
Yeah,
that would sort of explain both, because they all sort of approach that yellow line if you increase the width.
yes, this could also be a possible explanation. Yeah. Okay, then
For the other parameters, okay, so without multiplicity fluctuations also become sharper, right? It's everything becomes sharper, so mostly affecting the central region.
yes,
And the last two, what is the meaning of those parameters?
so
Subnuclear, I don't.
So the N basically means that you don't just put like neutrons and protons, but inside those neutrons and protons you have 4 constituents, and the V is the size of those constituents. So this plot basically means you have 4 small things in your proton, and this plot is that you have 4 larger things in your proton, for example.
But the physical effect is that if you have like central collisions, if you have like sharper nuclei with a smaller skin, with central collisions, you will have more complete overlap, so you have more participants, and this is why the multiplicity goes up for central collisions. Is that correct?
I think so.
I'm just trying to get the guess.
so if you have,
Makes sense. Yeah.
if your default parameter W is 0.4,
0.5. I think.
0.5, and the B is 0.4, that means your subconstituents are sitting basically completely on top of each other. They have no. So you have 4 times the same thing giving you the total.
Yes.
Whereas if you have a V of 0.1, then you can have.
Yeah, then you have-
density.
Yes.
Yeah, well, so what happens at the low multiplicity? So the yellow is different from all the others, like case 5, like that,
Yes.
close to the origin. We can
So they all mostly accounted for by the skin, change of the skin, because there's a conservation, right? If something goes up, other places have less probability, so if you change the skin thickness, basically that drives down the peripheral region. The number of events is less because it goes to the mid-central. There's more events in the mid-central and less events in the
I
peripheral.
don't quite understand what you're saying. So the observation I think here is that all models except 5 show a suppression below 1 by 4%.
Yeah, that's because of the change of the A. Once you change all case 1, 2, 3, 4, they all have a smaller A.
Yeah, and why does that suppress the ratio at low multiplicity?
Because the total integral of the distribution is 1. And so means if you have more probability that have events in the central region, those probability must come from somewhere else, right? So basically like, basically there's less events in percentage wise, less events in the peripheral region and a little bit more events in mid central region. It's a pure geometrical effect, I would say.
So what's the denominator? What is the
Case
denominator?
6.
Case 6.
Yes, it's the histogram of the zirconium collision.
If the denominator is case 6, why there is a sharp decreasing, sharp increasing in the central region. Case 5 divided to case 6, the
Yeah,
size
that's
changes.
because that's just the size
But
effect.
size changes for the same energy position. You have large size. You need to have a small N charge. Why increase?
So the question is why this goes up.
In the most central region. Right?
Yeah, in the most central region, the only changing is size. So your numerator is a large size, your denominator is a small size.
Yeah.
Why the N charge is increasing?
Yeah, I think it's just because the it's what matters is the ratio. It's a very because it be that it's the ratio of the skin to the radius that matters, and this slightly decreases.
But their skin, the other parameters are same.
Yes, but the ratio, but I think what matters, what really says how sharp your nuclear surface is not the skin itself, it's just the skin divided by the ratio. It's dimensionless quantity. Well, it's tiny effect, but maybe this is just good to see.
Yeah, we're really talking about the tail here, really like you're sitting on the exponential falling region, and that probably we're talking about that 0.1% region, like very, very simple, extremely
In the,
sensitive to whatever smear you put in.
in the case where you have a more diffuse edge, when you have full overlap, zero impact parameter, the probability of having full overlap of all the nucleons is lower because you could have some little straggler out here that it's more likely to have some unpaired spectator in that case compared to if you have a sharp fall off where they're all densities more concentrated. Does that make sense?
So should we maybe go on and then can discuss this
Yeah, let's,
in the afternoon, maybe a bit more,
Why not?
all the intricacies of moving up and down.
okay.
Okay, so
Click on the,
Click on the screen, on the
you were
keyboard.
playing around with the, yeah, just make sure the focus is on the slides.
okay, good. Okay, so now this is exactly the same plot, but now it's not the ratio of the histograms, but of the epsilon2, so this initial eccentricities. And what you can see here is, again, now we have to look at different cases. We now need to look at case 2, 3, and 4, where the beta 2 and the beta 3 changes. And you can see here that so case 1 and 2 I have the same initial deformation, so same beta 2 and beta 3, but they have a different gamma. So case 1 has a gamma of 30 degrees, all the others have 0 degrees gamma. You can see that here the blue and the red are perfectly on top of each other. So the eccentricity, or then also the flow coefficients, are not sensitive to this triaxiality. And what you can see again is that the radius, basically what changes from case 5 to the baseline to this case 6, and the rest is also not really playing a big role in this ratio of the eccentricities. But what you can see is that the case 2, 3, and 4, they differ by a lot. And this basically comes down to the change of not just the beta 2, but also the beta 3. And if we now go to the epsilon 3, so the next eccentricity in this harmonic ordering, you see that we have a grouping effect. So here we had 1 and 2, and then 3, 4, and 5 were somewhere else. And here we have 5 again as basically at 1. And then we have this grouping of 1 and 2 and 3 and 4. And the reason for this now again is those have the same beta 3, 1 and 2. and 3 and 4 also have the same beta 3. So you see the epsilon 2 is influenced by the beta 2 and the beta 3, but the epsilon 3 is only influenced by a difference in beta 3. And as a next we can look at this row 2 correlator, and this is now just a preliminary slide with the absolute values to maybe warn you that all of those quantities have a sign change from minus to plus, and the sign change, the x value, so the multiplicity of the sign change depends strongly, in this case, on this Trento parameter W. And this is the reason why you have those wiggly effects in here. Those basically come about from dividing basically 0 by basically other 0.
There is no data here.
Sorry?
There is data for this ratio.
No, we have
So
You have data, but you it's not.
I mean, you have to dataset it from the class outwards. So, yeah, we have all the data. Trend. But you know, the error bar is much bigger actually for this in the isobar. It's very difficult to measure.
I see.
okay, and so now, as I explained before, the biggest effect or the most you can gain from looking at this row correlator is actually when you look at the centralmost collisions where you have either this body-body or this tip-tip collision. And if we now look at here, we can actually see, for example, here or here, but the most pronounced cases are actually without the multiplicity fluctuations, and when you have this large W, that this is now basically the only time where you have at high multiplicity a visible split between the red and the blue. So this observable is, as we expected or as we hoped in the beginning, is really sensitive to the gamma of your nucleus.
Case 1 and 2.
Yes, so the
Case 2 have a is prolate. The case 1 is a triaxle, right? You compare the
Yes.
triaxle with prolate. So prolate should be low, right?
But you get this large difference only for somewhat unrealistic situations, right? W 1.2 is now, I think, considered to be large.
yes.
Ignoring the multiplicity fluctuations is definitely wrong. And so
Yes.
we should look at the default situation for
Yes.
one.
So there you still get a split between the red and blue, but it's not as pronounced.
Or
And
still, I mean, your scale is very big, so you go from 0 to
yeah, that's true. The scale is very
scientists
big.
are more than 10% effects.
Probably, and I guess the reason why it's bigger in especially those two cases is because then you really have probably like your nuclei are now really smooth objects with well-defined shapes that you collide. So if you have a difference in this gamma, this now really gets pronounced and comes out. And on the other hand, if you have like here this fluctuating, more spiky QGP or fluctuating nuclei, then those effects get
Can
washed
we
out
go
a
back,
bit.
see before taking the ratio, I mean,
To here?
yes.
Yes.
So,
I mean, yeah, so
Why
here you
is-
have this case 6 you have now, so the colors are the same, but case 6 is now the what is it? Zirconium absolute
so
value.
when you W equal 1.2, it's really like the value is totally different, right?
Yes.
From all the rest.
Yes, that's the reason why here, like you have this zero crossing with the spike always at low multiplicity, and here you move it up by like, I don't know, 100 units of multiplicity or something like that. Okay, so, and this concludes the first part of my talk, where basically we see that some observables are sensitive to certain nuclear parameters, like the histogram ratio to the A0, the V2 and V3 to the betas, but in a different way, and the rho to the gamma. And some Trento parameters can also affect those ratios by, again, what I call this degree of sharpness of the QGP, which basically come down to this nucleon width, the thickness P, and this constituent size. Then maybe one question for later on is then which is maybe the smallest set of observables that is the most sensitive to those nuclear structure parameters, since that's what we are after, but is the least sensitive to collision parameters, like that you don't get a big influence, for example, from this W. And what maybe is also to be kept in mind with this discussion is that, I mean, you can choose something like the rho or even go higher, fancier in like, I don't know, 4 particle observables, 5 particle observables, but there you always have to pay the statistics price. So this you maybe, or we should also have like in mind when discussing this.
Can you remind me, or I don't know whether you said it, when you said that the E3 or the epsilon 3 is affected by both beta 2 and beta 3?
No, this is the
Ratio.
this is the epsilon 3 ratio, and this is only affected by the beta 3. So this is the epsilon 2 ratio, and here you see between case 3, 2, and 4, you see green, black, and yellow have different.
What's the mechanism for that? I would have actually assumed that if you increase beta 2, you make the geometry more deformed. That limits the triangularity that you can put in there, so you would have this negative correlation between epsilon 2 and epsilon 3. But you don't see that here.
No.
You only see something in the epsilon 2, but how does the beta 3 affect the epsilon 2?
Stringy showed some cartoon right, yesterday that the problem is that this is a global geometry, it's not fluctuation driven data.
Okay.
The contribution to epsilon, or epsilon 2 or epsilon 3, this is all global geometry. And so if you segregate it, if you stack 2 triangles, I would imagine, right, you would tend to align the long side. That will give you a beta 2, epsilon 2 contribution. If you want to, in the mid, so in the global calculation, the impact, if you do not have a lot of multiplicity fluctuation, you will see that in the ultracentral correlation, beta 3 do not influence the epsilon 2. What it only start to have matter when you go away from the central correlation. So therefore, where you do it is that you stack the 2 triangles, which would look like in this shape. Right. So that's how I interpret this feature.
I mean, you kind of can see.
But once you have a multiplicity fluctuation, actually the impact also appears in the central correlation. But the one, if you see the without multiplicity fluctuation, the difference between the green, which is only the beta 2, and the red, which is both beta 2 and beta 3, you see there's still some impact in the central, but it's less. Yeah. If I be in N part, actually the difference you will see. But if I start to be in the final state multiplicity, the smearing effect actually.
I have thought about this longer than I, so my intuition is not yet developed.
Okay, but so I also have, for example, the rho 3 epsilon 2 4 initial energy system size for discussions later on. So we can also look at different those observables and see if we maybe can come up with an idea of this set of observables.
Just to remind me, you're saying the higher cumulants are statistically demanding. Are they worse than this row?
No, my point was not that they are worse. My point was just that, I mean, you can, what you in principle also can do is just to say you fit basically, or you look at every observable there is on this planet, and then you get a maximum content of information. But then, I mean, if you run Trajectum with, I don't know, like 200 observables, it will never finish probably. So you should probably try to come down to a smaller set of observables. And then if you choose them from like what I gathered from yesterday, fitting or running hydro or getting sensible results for something like a PT, mean PT, or even V2 is easier than for like this row 2 correlator, right? Or this row. So because I mean it's
but once you have, if you decided you wanted row and you had those events, then I don't think it adds anything to add a
no, I mean if you already have no,
I don't think that really adds anything. Once you
But
have the
if you
events.
want
No.
to, depends on what you want. If you want to gain some information on gamma correlator, you definitely there's only two observers which you can use, right? Which is, they all involve more than two particle correlation. But if you want to get a beta, a beta 2, beta 3, then two particle observers are probably sufficient.
Yes. So,
And also the single particle observer, of course, goes together.
So then, I mean, if you're just interested in like beta 2, beta 3, you can look at like V2, V3. You run, I don't know, 50,000 hybrid collisions or something. And if you want and get enough statistics, and for the row, you might need to run 100,000 because it's a 3 particle observable. But of course, if you have the events, then it's no problem at all. Okay, so if there are no questions or comments to this part, I would say
There's no chance for it.
I probably should keep going. Okay, good. So, and as a second part of the talk, I want to quickly introduce a different hydro framework, which I used to basically verify for the histogram ratios, what we already found as like dependence on Gentile parameters, nuclear structure parameters, but also vary on top of that the QTP parameters like viscosities or freezer temperature. And this hydro framework is both based on the mode-by-mode hydrodynamics, where the idea is that we don't describe a single event, but we describe an event ensemble. And what this basically means is that we take the event average in one given centrality class, and this allows us to introduce a statistical symmetry. This basically comes down to what Jean-Yves talked about in his talk, where he, I don't remember the year, like 2000, 2005, where you developed this hydro code for B equals 0, because then you have like rotationally invariant.
Yeah,
Sorry?
not even the right decade.
Oh,
Not to make
yeah.
him feel old, sorry. saying.
Yeah, no, I mean, I already learned that some of the participants here were at the quark meta before I even was born in Heidelberg. So, yeah. So basically, the idea here is that if you take a lot of those are of course simplified profiles, but if you take a lot of those like oval shaped profiles and then you add them up and rotate them by a random orientation, what you will get at the end as an average is something that's rotationally invariant. And this allows us to split our hydrofields into a background that only depends on the time and the radius, plus some perturbations on top that depend on all 4 fields. And so this means that we get 1 + 1 dimensional equations of motion for our background, plus some linearized hydro equations for the perturbations on top. And in this framework, because we already do this event average at the beginning, the background quantities, or what we calculate from the background, are event average quantities such as yields or the mean PT, and the quantities we calculate from the perturbations encode the fluctuations. So we quantities like flow harmonics and the Pearson correlator are calculated from those from the perturbations.
The fluctuations also, I mean, the fluctuations contribute to hydrodynamic entropy production, to viscosity. And so they change the non-electricity.
Yes, but in this framework, so they don't, in this framework, how we define those expansion parameters, they don't contribute to first order, they only contribute to second order in perturbations. And for now, we only go to linear order.
So this is entropy for them.
So
So when you average over the fluctuations, the average.
Yes.
The leading order cancels out. Sort of by construction.
yeah, so basically the way we do this splitting up is that the one-time function of like this weights, when you do the basis expansion, the one-point function is 0, and then your fluctuations are encoded, for example, for the V2 and the 2-point function or the higher order moments.
Oh, I guess you're saying the entropy production fluctuates, that you're saying? Yeah, okay. That should be true, right?
So
Maybe keep going.
yeah, I also have a slide later where I can show you how we do this with the basis, then we can maybe discuss about it again. And yeah, so and this code package is called Fluidum. It's a Mathematica and now also Julia implementation, which we are going to make public soon. And we basically have what I've shown you before. We have hydrodynamic equations plus second order Isol-Stewart equations the evolution does not violate causality, and it's violated against the Kupser flow. And I will show you another validation next slide. And then the particlization, so this freeze out plus the resonance decays are done by this Cooper-Frye equation I've shown before, plus the fast reso under that, so this fast reso code developed by Alexas.
So question.
Yes.
This 1 + 1 dihydro equation is not full 2 + 1 or 3 + 1, I mean 2 + 1 dihydro. So but how can you model fluctuation? It's 1 + 1.
It's so 1 + 1 is like spatial dimension. So we have time plus the radius.
Okay.
And then so
That
this
is only for the smooth background. So
yes, this is for the smooth background, and then the perturbations are also 1 + 1 dimensional, because what we do is you have time and radius, and then you do a Fourier transformation in the angle and rapidity, and then you get basically you get modes that have quantum numbers. So you then get like 1 + 1 dimensional equation for the perturbation for, let's say, the m = 2, k = 0 mode, something like that. So, but the fluctuations are still included. Okay, and then just to show you that this is not just all a hocus pocus, we took the results from the first Bayesian analysis of the Q group from this paper and basically matched their equation of state, their viscosities, their freeze-out temperature, or in their case, they had a switching temperature because they moved from hydro to a hadronic afterburner. And the results look like this. So on the right-hand side, you see the results of the Duke group, with the solid lines being their theory results and the points being the Alice data. And on the left-hand side, you see the Fluiden results, and you see that especially for the n-charged, I don't know if you can see it from the back, maybe you can see it on the screen, but this, like the theory to data ratio is basically 1, and it's the same agreement with the Duke.
Go back. Like,
Yes.
was there a reason you didn't use like exactly the same viscosities? Why are these different?
Yes, so you see that the Duke group here, this is 0, and then their viscosity like that, because so the difference is this is based on how they call it, like this I forgot the name of the numerics, but basically in our code we evolve every point of our grid in radius until every point is frozen out. So we also evolve like a point at r = 30 Fermi that has already frozen out. And if we then have like a negative viscosity or some weird stuff happening with the viscosity at like those low temperatures, we run into problems. And the Duke group, I think if one cell is frozen out, they don't compute like the time evolution of the cell anymore. So for them, it doesn't matter what happens at low temperature.
But the bulk then?
The bulk is, which is ours. I think this is for like causality reasons. This is and also for running, because I mean the freezer temperature is here at 148, so this is here. So basically this peak that dominates the evolution is the same. And what happens here, I mean, this cannot influence the results because in our case it's frozen out, cannot propagate inwards, and in the Duke group they don't even evolve it anymore. Yes.
Duke group actually does something different because they, I think it's 0.14 GeV, but the exact number could be wrong. At some temperature, they switch to constant eta over S. Different from.
It could be that they like switch here to 0.
No, they don't switch to 0. They switch to a finite value, which is constant.
I think 0.08 actually. I think it's discontinuous.
Yeah, it has the potential to be discontinuous. Yeah.
Okay.
It's a separate parameter.
Okay.
It's easy to miss in the paper too. I think I did it the first two.
Yeah,
That's what
but
they're doing.
so anyways, if they use also discontinuous like eta over S, that's also not good for our implementation. So we basically smooth those functions out a bit, and also this like has some job. Okay, so and with this setup, we now want to look at the n-charge ratios instead of the histogram, like the multiplicity histogram ratios. And what we do, or what I did in this case, is I run again Trento for the initial state and define 0.5% centrality bins using 50 million minimal bias events. And then I select a few of those centrality classes, I'm not interested in the full range, and run 400,000 events in this 0.5% bin, which means that I have an effective statistic of 80 million minimum bias events. And then I do this for basically the parameter set I've already shown you before with like nuclear parameters, Trendo parameters, and parameters like UDP parameters like viscosity, freeze out, temperature, and initialization. And so those are from this calculation, again, the initial state results with like the histogram ratios where you see again, so those are all the different Trendo parameters with the data. Those are the nuclear structure parameters. And here you should look at the green and the yellow, where you see the yellow is same nuclear spin and green is inverted, so that the ruthenium has the bigger neutron skin compared to the zirconium. And this is the only case where you can invert this bending and don't have the same trend as the data.
The color is hard to read. I mean, which one is the blue A zirconium bigger than A?
So the blue one is this line here. Then the yellow is when they have the same A. The green is where the ruthenium has the larger A compared to the like how it should be. And then this red one is where the nuclei are fully round. And the purple one here is where we basically changed the radii, where we made the zirconium a little bit larger and the ruthenium a little bit smaller compared to what they should be.
So the difference between blue and the red is the impact of deformation, which is tiny, right?
Yes. And then we can now put those in our mode by mode hydro, where the benefit is now that we only have for one centrality class, I only have to run the hydro once, and then I have basically the results with this 80 million events as statistics, so basically no statistical error. And so here on the bottom, you see, you always see the centrality on the x-axis and the n ruthenium divided by n zirconium ratio. And here you can see what already was a bit discussed, I think, on Tuesday, maybe Monday, how now in the hydro, those isobar ratios depend on our model parameters. You can see here we vary the freeze-out temperature from 140 to 145 to 150 MeV, and I'm very close to it, and I barely can see any spread of the data.
For those specialists, is 10 MeV a lot, or because it's 510 MeV, right? Different between 140 and 150.
Yeah, I would say that's a larger step. I mean, well, I don't know if like the others consider this a smaller step, but I mean, it's for like, if you just look at the multiplicity, like the raw multiplicity, you see a considerable difference between like 150 to 140 if you keep everything the same.
Which one produced more? The smaller freeze-out time give you more particles. Yeah.
No, the bigger one.
Bigger, if you freeze out early, you get more particles.
Yes, because then you basically the surface where you produce your particles from is hotter.
But the volume is
But it's a smaller surface.
smaller. So
It's a little less obvious.
And it like already some physical like ion mass or something. So,
No, this basically is this temperature where the switching temperature in the QCD phase diagram, when you look at like the mu equals 0 axis, this comes down to the temperature where you transition from your quarks and gluons as degrees of freedom. Then at some point it gets cold enough that you get confinement again, and you freeze out or you switch your effective degrees of freedom into hadrons. And this is basically this temperature.
The thing is, since it doesn't look like a big change of temperature, but since the density varies steeply with temperature, it means that well, when you go down from 150 to 140 MeV, it will increase the volume quite a lot. So it's not a ridiculous change. And I think it's but there is a compensation that if you take into account resonance decays, is that correct? I think a lot of these differences. So it's a good thing, actually. I think that we know that, well, we have to freeze out to stop the fluid evolution when we have hadrons. And we know that we switch from quarks and gluons to hadrons around 156 MeV. So I think it's a good news that we don't really know where to stop. So I think it's a good thing that, well, it doesn't really matter because the result won't change much because it's like a cutoff, you know, in the calculations. It's a arbitrary.
For each one of the nuclei, the results will change, the ratio doesn't change.
Yes.
I see.
Can you show maybe like how much multiplicity
But I think that
changes this with the temperature?
So I don't have to see it, but I can
After resonance.
take
After
for
Just
later.
quickly get that.
Yeah, yeah,
Makes
this-
sense.
Here you can, in the ratio, you can probably just even forget.
Okay. Because I was surprised actually to see how little changes when you take into account resonance decays, which is good news.
Yes. And so this is the same for this initialization time for the hydro, but since lunchtime is almost here, it's I'm also almost finished. So let's try to get it done on time. So here you see the same plot again, but now we vary here the zeta over S by a factor of 3 from 0.05 to 0.15, and here the eta over S from 0.08 to 0.32. And you see again that basically there's hardly any spread. So those multiplicity ratios are basically not at all sensitive to the medium viscosity.
So I can add something here. So basically, because one is plotting the centrality, which is sort of like self-normalizing, right? So we saw the same thing in AMPT where you vary the viscosity a lot. You also vary the hadronization, you know, how much the hadronic phase is. Basically, you can vary the multiplicity by, let's say, 10%, okay, the way you do it. But then if you rescale them or you divide by centrality, they all disappear. The shape doesn't change, basically. Right, so if you, whenever you do this, they all cancel
So
out.
what you're saying is that if you increase the viscosities, the multiplicities do increase because
Yes.
there is more viscous
Yes.
interaction. But the ratio, but they increase at the same rate in both systems because they have the same lifetime, same terms.
No, but even as a function of centrality, it's kind of, it's pretty constant.
Yeah,
It doesn't really change the shape.
because the shape is the same. Yeah.
Right. And
Another question.
Yes.
So, compared to experimental data, seems to have good friend is shifted. Why do you know why?
yeah, because this is now with just some set of gentle parameters, and this is not tuned to reproduce the data at all. So this is now mainly the focus is that we vary the QGP parameters and without taking into consideration the fitting the data with gentle parameters, because then you basically are back to when you touch something here with like the QGP parameters, you might need to change around the gentle parameters again, and you have to rerun all of this. So this would come down to kind of fit.
Isn't it that you don't have the right difference between skins because this ratio should depend on the.
Yeah, probably it's probably that we don't have the right difference between this. But this I can check. All right, and then if we now actually do vary the skins and the gentle parameters, you see again basically what we've seen before in the initial state, that the blue, purple, and red all have the same trend and basically lie on top of each other. And the only time when you can change around the trend of your multiplicity ratio as function of centrality is when you change the ordering or the relation of your skin thickness. So the yellow is again same skin, which you can see you basically are flat at unity. And the only time when you can start below 1 and bend it down instead of going up is when you invert the order of your skin of the zirconium and the ruthenium. And here you basically can see again what we were seeing before as well, that the only outliers we have here are this kind of, I don't know, brownish red, whatever, which is this W1.2. And you have this green and this blue, which corresponds to the P equals -1 and this M equals 4, V equal 0.1. So the ones that are where the ratio is above the peg of those curves is where you have a sharper QGP. Then you have all the versions with like the regular spikiness of the QGP, and the one that's flatter than all the others is the W1.2, where you have a smoother version of your
So you need the
QGP.
subnuclear degree freedom, right? You need this in order to bridge the.
Yeah, here again, I'm not sure. So those results are
No, I'm
I-
saying which one is the blue in the top peg? There are two curves. Which one is that blue?
this one is, I think this it
Yeah,
was
so
the
that's the
subnuclear
means you need
degrees
to
of
do
freedom.
quarks. Yeah. and
Yes, but
subnuclear.
I'm not sure which like nuclear parameterization we
Oh.
use for this, because those calculations I did now 1 year ago or something like that, so I would need to look this up. All right, so as a conclusion, we have seen that the different initial state predictors have varying dependence on the nuclear structure parameters. For example, the histogram or multiplicity ratio is dominated by this A0. That mainly this sharpness of the QGP has some influence also on your resolution, on your multiplicity ratios or general observable ratios, and that in general, at least for this one observable, we can say that the dependence of the Trendo and nuclear structure parameters we found in the initial state predictors carry over to this final state multiplicity. And as an outlook, we can now, or we want to extend this parameter scan to more observables, especially the final state, and also maybe more initial state predictors if there are new ideas. And we, of course, also want to now in our framework calculate V2, V3, all those quantities based on perturbations to confirm, and mean PT, confirm that what we found for like the epsilon 2, epsilon 3 ratio, to also confirm this with hybrid simulations for the final state observable. So calculate 2, 3, vary the eta, and hopefully find that they are again independent of the viscosities.
I think that's the effect. Can you go back? You said the increasing the steepness of the distribution gets you in the right direction. Which one is steeper?
Ruthenium is sharper. Yeah. So the blue is the right order.
Yes. So, yeah.